In a high-stakes tech interview, and the interviewer slides this prompt across the table. Design a service like Gopuff. It's a classic question for a reason, you know? It tests everything from your basic architectural chops to how you handle insane scale. So today, we're going to tackle that exact challenge together, from the very first question all the way to a final, scalable design. So here's our game plan. First, we'll define the problem, just like you would in a real interview. Then we'll lay down the basic digital foundation. After that, we'll build a simple first draft to get things working. And then, here comes the fun part. We're going to stress test it with real-world scale and find all the breaking points. And finally, we'll rebuild it into an optimized system that can actually handle the heat. So, you're in the hot seat, the prompt is on the whiteboard, the clock is ticking. What's your very first move? Do you start drawing doxes and arrows, firing up a database schema? I mean, where do you even begin with something this big? Well, the answer is you don't start drawing anything. Your first move is to start asking questions. Before you write a single line of code or draw a single box, you have to be absolutely crystal clear on what you're actually building. This is the most critical first step. It's all about clarifying the requirements. Okay, so what is Gopuff, really? It's not just another online store. The magic, the whole secret sauce, is the speed. And that speed comes from its hyperlocal model. They use tons of these small, local warehouses, micro-distribution centers, to promise delivery in under an hour. And that one detail, that's going to shape every single design decision we make. So, based on that, we can start to lock down our requirements. Functionally, it's pretty simple. Users need to see what's available near them and then, well, order it. But the non-functional requirements, that's where the real challenge is. Availability checks have to be lightning fast. We're talking under 100 milliseconds. Ordering has to be rock-solid consistent. We can never sell the same last bag of chips to 2 different people. Oh, and it needs to scale to 10,000 of these warehouses. No big deal, right? All right, with our requirements locked and loaded, we can finally start sketching out our digital blueprint. And that means defining the core nouns of our system, our data, and the verbs, the APIs that let people actually do stuff with that data. Now, right away, we hit a super important distinction: item versus inventory. Think of it like this. An item is the idea of Cheetos. It's the product page, the description, the picture. Inventory, on the other hand, is the actual physical bag of Cheetos sitting on a shelf in a warehouse in Brooklyn that you can buy. One is a catalog entry, the other is a real thing we can sell. Getting this distinction right is absolutely fundamental. So, to make all this work, our whole system really only needs 2 front doors. First, a get endpoint for availability, where a user's app can ask, hey, what can I buy right now near me? And second, a post endpoint for an order to say, okay, I want to buy these specific things. That's it. It's simple, it's clean, and it maps directly to what our users need to do. Okay, the foundation's set. Now it's time to sketch out version 1. Look, the goal here isn't perfection. We're not trying to build for massive scale just yet. The goal is to get a simple, working design on the whiteboard that does the basic job we need it to do. So let's follow a request through this first draft. A customer opens the app, which sends their location to our availability service. Now, this service is a little lazy. It doesn't know where the warehouses are, so it asks a buddy, the nearby service, hey, who's close? The nearby service sends back a list of local warehouses. And only then does the availability service check the database for stuff in stock at those specific locations. This is a really smart separation of tasks, because it means we're not searching the inventory of the entire country for every single user. Okay, so finding items is one thing, but selling them correctly? That's where things get really, really tricky. This is the classic concurrency problem. What happens when 2 people, at the exact same millisecond, both hit buy on the very last item in stock? How do you guarantee only one of them actually gets it? We're basically at a fork in the road. We could use different specialized databases for everything. Super flexible, right? But it opens a Pandora's box of horrifying failure scenarios. Like, what if your service crashes after it creates the order, but before it updates the inventory count? Yikes. The other option is to use a single, reliable database like Postgres and use something called an ACID transaction to wrap the whole operation together. It makes it atomic, meaning either the whole thing succeeds or the whole thing fails as if it never happened. Now, here's a pro tip for any system design interview. When in doubt, always go for simple and correct. Trying to manage distributed transactions is a nightmare, so we're going to choose the single Postgres database. By wrapping check inventory, create order, and lower the inventory count into one transaction, the database itself guarantees we will never ever double sell an item. It's clean, it's robust, and it just works. So we have a working design. High fives all around, right? We're done. Well, not so fast. Now comes the part where we really pressure test this thing. We're going to take our nice, simple design and see what happens when reality and all those non-functional requirements come crashing in. Remember that little requirement about scale? Let's do some quick back-of-the-envelope math. For every one person who actually buys something, you've probably got way more just browsing, right? When you run those numbers, you end up with something staggering: 20,000 queries per second, hitting our availability service. Our simple little database design, it wouldn't just slow down, it would literally melt. So our stress test just blew up two major parts of our design. First, that nearby service is way too simple. Calculating distance as the crow flies is useless when you have real roads and traffic. And second, and this is the big one, that 20,000 queries per second read load will completely vaporize our database. We have to solve these two problems. Okay, time to put on our architect hats and re-engineer the system for the real world. This is where we start applying some classic, battle-tested design patterns to solve for speed, for throughput, and for correctness. First up, let's fix that nearby service. Instead of doing something complicated for all 10,000 warehouses, we get smart. We do a quick, cheap first pass. Just give me warehouses in a 60-mile circle. Then, for that much smaller list, we make a call to an external service that actually understands roads and traffic. It's way more efficient and a whole lot more accurate. Okay, nearby is fixed, but we still have that elephant in the room. 20,000 read queries every single second. This is the biggest challenge of the whole design. How on earth do we shield our database from this absolute fire hose of requests? The answer, as it so often is in system design, is caching. We're going to stick a super fast, in-memory database like Redis right in front of our main database. It's like a short-term memory for our service. When a request comes in, we check the cache first. If the answer is there, that's a cache hit. We send it back instantly, without ever bothering the database. If not, we go get it from the database, and then, this is the key, we store it in the cache for the next person who asks. But of course, every solution creates a new problem. With a cache, that problem is stale data. We can't have our cache telling people an item is in stock when it just sold out. We solve this in two ways. First, we set a very short time to live, a TTL, of just 1 minute on everything in the cache. And even more importantly, whenever our orders service processes a successful purchase, it has to immediately tell the cache to invalidate or delete that item's entry. This keeps everything nice and fresh. Now, caching is our first line of defense, and it's a huge one, but we can go even further. We'll introduce read replicas. These are exact copies of our database that only handle read requests, which frees up the main database to just focus on taking orders. Then, we can partition our data by region. It's like splitting one giant phone book into smaller, city-sized phone books. A query for Chicago will only have to look in the Midwest partition, which makes it incredibly fast. And there you have it, our final, battle-hardened architecture. We've created this layered defense system, caching, read replicas, and partitioning to handle that insane read load. Meanwhile, all the really important write operations for orders go to a single, transactional main database, which guarantees our orders are always correct. We've solved for both speed and correctness, at scale. So we did it. We designed a pretty robust system for finding and ordering stuff. But here's the secret about system design. You're never really done. What's the next bottleneck? What happens when it's Black Friday and the number of orders spikes, crushing our write database? Or what about the completely separate, incredibly complex system of routing thousands of drivers? The real question, the one every good engineer keeps asking, is always, what's the next problem to solve?